Okay, so thank you everyone. We might just get started in the interests of time. So thank you everyone to coming to... Thanks everyone to coming to this fascinating session that we're going to have hearing about some of the latest research across a few very exciting different subfields. And so without ado, we might welcome Professor Claire Wainwright to the platform. So Claire is a paediatric respiratory physician at Queensland Children's Hospital and co-lead for the services there, and she has a wide range of fascinating research, and we're very looking forward to hearing what you have to say. Thank you.
Well, thanks very much, and thanks for the opportunity to talk to you today. I feel a little bit sort of nervous about doing this because actually I know nothing about gene therapy or gene editing. I know a little bit about modulator therapy, but I'm going to try my best to run through this and hopefully at the end of it you won't ask me too many very awkward questions. Now, this picture was done by one of my or not one of my patients, one of our patients at the Queensland Children's, who's had a very rough trot and has been in hospital for around 6 months actually. And this young man smiled at me when I asked him if he would do me a picture. And I explained that I was giving some talks and that it was around the sort of changing phenotypes or changing approach to cystic fibrosis. And he's done this lovely picture, and you can see he's written, "Things can change." So hopefully things can change for lots of people with cystic fibrosis, right across different genotypes. So I do have some disclosures that are relevant to my being here, so I'll leave that up. I've been a consultant for Vertex Pharmaceuticals and an investigator in many clinical studies. Now, I thought I'd just start with this, just so that everybody's got their sort of feel about how things work. Now, what we find with genes is that basically it's a code, and it's a bit like I kind of describe it to children and young people as there's a code there that's going to sort of basically describe who you are. So it's going to give you the colour of your eyes, the colour of your hair. It's going to really determine all sorts of things, including, who you are and why you're different from other people. But it doesn't give everything. But it is important to understand how it works. So what we've got, I'm going to see whether this, I'm not sure if this is going to work here. I won't be able to see over there. Oh dear, I'm going to struggle with this bit. So, can I do it against this? No. All right. We won't be doing that. So if you look at the top part of the slide, what you'll see is that you've got these two, you've got the grey bit and you've got the pink bit, okay? Now, the pink bit, the pink sort of bit with the teeth coming out of it, is the kind of copy of the gene that it's copying. Now that has to be, if you like, chopped up and made into a very nice message, and then you can see underneath you've got that grey arrow coming down. Oh, whoopsie, I'm going to really struggle with the technology, aren't I? Okay, I can't cope without doing a bit of playing. So there's an arrow coming down. Now you've got your lovely message here, and that is able to go and form the code that goes into the factory of the cell, this little beastie here, the ribosome, and the message goes through, and this little ribosome can translate that message and turn it into a protein. And that's incredibly clever. Now, all sorts of things can go wrong with that, of course. So you might have a code here that delivers a protein with a message that basically makes this protein not work and it gets dumped in a bin. Or the message has a little stop here and out comes a protein that's too short and again doesn't work at all. So you might have a protein that could be rescued, you might have a protein that is beyond rescue, and you might not make any protein at all because this whole system falls apart. So there are all sorts of issues that can go wrong with this. Now, I'm not going to dwell on this bit, but this is called splicing, and here there can be mistakes as well. So what we've got at the top here is effectively the cutting and chopping up of these bits of code and reforming them. And you can see here that these messages effectively can lead to different proteins. So if you chop these up and put them together in different ways, this sort of splicing, if you like, you can translate these into different proteins. So if you've got this going wrong, so splicing variants, you can end up with a protein that doesn't work or nothing at all. So that's where it's very important to understand how these genetic problems are going on, because of course in cystic fibrosis all of these problems can exist. Now, gene therapy. So gene therapy, there are different forms of gene therapy, and the way to think about this is integrating, so you can actually put a correct CFTR gene that gets actually put in to the genome. So let's go back. And now think about this bit. If this is all correct and you've got the right protein coming out here, you fixed it, okay? So if you've got an integrated, normal genetic code, then out comes the right protein. That's fantastic. See? Oopsie-daisy. But if you do that, then that could be permanent if it's in the cells that are just going to keep on reproducing. But the trouble with that is that it's not straightforward. And there are other ways to also get at this, where you can get a piece of the DNA with a correct copy of CFTR that's delivered, but it's not actually incorporated into the genome, so it's not there permanently, but it can still make the cell make the right protein. Now, these are the mRNA therapies, and I've pinched this picture from the CFF website, and in fact my tip is to look at the CFF website because there's some fantastic videos that run through some of this technology. And this technology is really rapidly expanded because you've all heard of mRNA COVID vaccines. Now, with this, what happens is a message is delivered to the protein factory of the cell to correctly make the CFTR. So very important. Now, there are some advantages. This doesn't integrate, so it's much less risky. The technologies are already really very well advanced, so that's cool because of COVID. The disadvantages are that mRNA is rapidly broken down in the cell and it may not last long. So targeting, and you may not get into all the organs in the body. So if you're targeting the lung and you have an inhaled mRNA, you've got challenges with getting through mucus, getting through all those layers into the right part of the cell. And in fact, even getting to the right cells. So there are all sorts of challenges with doing this, but we think it's probably going to be the quicker way forward. Now, what about gene editing? That's where you get that integration. So that's where you change the abnormal gene in the cell DNA permanently. And that uses the tools in the cell to really do this work. Now, that technology is already available in animals, and there have been some rather unethical studies done in humans from China. There's some babies in China who had some of this done, which was regarded as rather unethical at the time, and you might have seen some of those news stories some time ago. Now, this technology uses something called CRISPR, and that really takes a guide to find the abnormal DNA, so to find that little bit of code that's abnormal and that needs to be corrected. And then there's a sort of template that really gets that correct sequence of DNA, and you've got little scissors that cut the abnormal bit out and integrate that nice normal bit. So effectively you're really editing that bit of code. So that's fantastic. Now those are the website links to have a bit of a look if you're interested, and that will give you a much better idea than my talk. Now there are some advantages to gene editing. It's permanent, and the technology is advanced in animals. However, there are disadvantages. It's permanent, so if you make a mistake, you've got a permanent mistake. And mistakes, unfortunately, are still possible, and they could also lead to risks. So you might edit something and then get an increased risk of cancer, say. Now, the other thing is, to get the cell to help you do this, you need dividing cells. And in adults, that's a little harder to do. So successful therapy for this remains somewhat far off, but I think it will come. Now, what about the actual gene therapy? Well, gene therapy is really where you take the gene, the DNA, the correct DNA, and you supply it to the cell. So you're putting it into a genome to replace the faulty gene. And there are some approaches that have already been used for cancer, for example, and for other conditions. And so there are eye conditions, for example, that are being treated with gene therapy. So it's been successful for some therapies, for some diseases. So far, this has been quite challenging in cystic fibrosis, and delivering gene therapy in CF has been very tricky, and you've actually got an expert in the room, far more expert than me. So Adam Jaffe's been involved in gene therapy trials, but it's difficult to do. Now, delivery to the lung really involves getting through all those layers, the mucus, etc., and getting that gene into the cell. You have to also avoid inflammation, because if you're delivering those bits of DNA, those cells turn over and that might not last. So you might need to do it again. So if you're going to do it with viruses, you need to use viruses that are going to not cause inflammation. And can we restore this body-wise? Well, very tricky. So this is the pipeline of genetic therapies on the CFF website. And just a quick word on new modulator therapies. So lots of patients don't have modulator therapies that are fixing their problem, but there are some new ones coming down the road. Now, Elox Pharmaceuticals are particularly interested in those what we call nonsense variants, where you've got these X's that cause those very shortened proteins that really can't be rescued. And so some of these studies are underway. Southern Research are looking at really screening drugs to see what can be done. And Sionna Therapeutics have taken a different approach and are looking, if you look at this, the sort of picture of the CFTR protein there, they're trying to fix different parts. They're trying to target different parts. So that's another interesting way. So there are all sorts of things that are being done to increase access and improve outcomes. And if you look on the clinical trials website, what you can see is that there are studies that are looking at treating drug efficacy through N-of-1 trials, so that'll be very interesting. That's where one person is who looks like they might respond to a drug, gets a drug for a period of time, you see if they respond. Then there are some treatments that might make actual modulators work better, so that's very exciting. And there are some new modulators that are being put together as well. So there's this diracaftor, posenacaftor, nesolacaftor that's being used in people with genetic problems with the standard modulators, but who have looked like they might benefit from these drugs in organoid studies. And then there's targeting inflammation again. So really there are all sorts of different approaches, and this is, I think, a really exciting future. And this is another little person who is in hospital at the moment, who's had a very, very tough time, and he and his mum put this together, and you can see the sun rising, the sun in the sky in the middle of the day, and the sun ending. And he thinks that the one thing that is always going to be the case is that change will always happen. And so that's how he put his picture together. So I think it's an exciting time. Thanks.
Thank you, Claire, for that very informative speech. And I think it's really important that we understand the basic information about where all these therapies that are talked about. So it's really good to see some of that science behind it. And we're certainly not experts, so you're definitely the expert in this room, so thank you. Our next speaker is Dr. Jagdev Singh. Dr. Dev is a paediatric pulmonologist and sleep medicine physician at the Children's Hospital at Westmead. He's currently pursuing a PhD focused on the study of bacteriophages in children. Dr. Dev initiated and launched the first clinical trial in the world involving the use of these viruses to treat lung infections in children with cystic fibrosis, and I'd like to welcome him to the stage. Thank you.
Good morning, everyone. Before I start, I just wanted to express how grateful I am to be able to have this discourse with all of you this morning. I will be talking about a story about mold and sewage, and I assure you it will make sense as we go forward. Now, humanity, for thousands of years, we have known that there is a property in mold that helps us fight infection. Now, in the Aboriginal community, they used to use mold from eucalyptus trees to treat skin infections. The ancient Egyptians used mold from moldy bread to treat pustules and skin infections as well. And if you are fluent in ancient hieroglyphics, you can actually read the recipe from the Ebers papyrus, although there are translations for it. The Greeks used to scrape moldy cheese to treat injured soldiers. The Chinese, they use moldy soybeans to treat skin infection. And in the first millennium, there is a recipe in the Talmud for moldy corn mash in wine. And scientists, they have found traces of tetracycline, which is an antibiotic in the bone fragments of Nubian soldiers thousands of years ago. Now, it is in the turn of the 20th century that we started to encapsulate or understand the concept of antibiotics. In the early 1900s, the first synthetic antibiotic was discovered and produced called Salvestin, and it was used to treat syphilis. And we all know the story about the chance encounter Alexander Fleming had in finding penicillin in the late 20s. But when he found penicillin around the same time, there was already reports on the resistance against the first antibiotic that we found, Salvestin. And by the late 1940s, when he received his Nobel Peace Prize, Alexander Fleming actually already started talking about resistance against penicillin. And this is an excerpt of his speech. Mr. X has a sore throat, he buys himself some penicillin, gives himself not enough to kill the streptococci, but enough to educate the streptococci to resist penicillin. He then infects his wife, Mrs. X gets pneumonia, treated with penicillin. The streptococci is now resistant to penicillin and the treatment fails, and unfortunately Mrs. X dies. And that seems to be almost like a prediction of the years to come. In the mid-70s, the first evidence of golden staph, or MRSA, was first detected. And by the year 2000, there was alarm bells going on all around the world about we need to do something about these superbugs, these resistant organisms, and it is a fundamental threat to humanity. So much so that in 2019, 1.5 million people perished from a superbug infection simply because there wasn't any antibiotic that was effective to treat those infections. And by 2050, there will be 10 million people who will die every single year from a superbug infection. And that will surpass the deaths from cancer as well as cardiovascular heart disease. Now, antibiotic itself, it is within their nature to develop resistance. However, because of the mass production of antibiotics in the past 120 years, we have accelerated this resistance. And how do antibiotics develop resistance? The first thing is they keep antibiotics out of their cell wall by creating thicker walls or biofilms to surround itself. Or if in the event an antibiotic actually enters, they've created pumps that pushes out the antibiotics so that they do not cause any damage, or they in fact hide certain parts of their cellular wall to camouflage itself so that the antibiotic will not be able to set itself onto the bacterial cell, or simply produce substances or enzymes that break down the antibiotic. And this war is ongoing, it's accelerating. And why is it important in cystic fibrosis? We are, in the cystic fibrosis community, pretty much in the forefront of this war, because by nature of the disease itself, patients living with people living with cystic fibrosis are exposed to infection and therefore repeated antibiotics. By nature of the airway itself, there is an altered electrolyte level, thick mucus, and also ineffective inflammatory response that renders the fight against infection poorer. Now, with the advent of ETI, modulator therapies, we are seeing the landscape of cystic fibrosis change. We are seeing an improvement in lung function, improvement in weight, better quality of life, but we are not necessarily seeing a total disappearance of infection. We are seeing a reduction in pulmonary exacerbation, a reduction in bacterial density from airway samples, but it's still there. The inflammation is still there, albeit in a lesser level. So that just means that this war is not over, and we are still in the front lines fighting a raging war. Now, this is where the sewage part of my talk comes in. Before the turn of the 20th century, researchers were starting to discover antimicrobial properties in the river, the water from Ganges River. And in the 1920s, just before Alexander Fleming discovered penicillin, Felix de Herelle described this phenomenon, and he attributed it to bacteriophages. And then they formed an institute in Eastern Europe, in Georgia, in the 1930s. Of course, then the Cold War happened, mass production of antibiotic. People sort of forgot about bacteriophages until recently, when there is a resurgence in interest and therefore clinical trials in bacteriophages. Now, what are bacteriophages? These are naturally occurring viruses that are the most common organism in the world. For every grain of sand there is 1 trillion bacteriophages. And as its name suggests, bacteria, phage, to eat. Bacteriophages are bacterial predators. And the clinical trial that we are currently doing is the world's first clinical trial looking into the safety and efficacy of bacteriophages in the use in children infected with Pseudomonas aeruginosa. And our question is whether or not it is safe and tolerable. We need to start from scratch to make this therapy more accessible. And we've developed a protocol. In the interest of time, I will skip this. But let's talk about the progress. So we've treated three teenagers, 12 to 17-year-olds, and they've had Pseudomonas in their lungs anywhere between 6 to 11 years of their life, multiple admissions for pulmonary exacerbation, 11 to 13 times for each of them. We did not find any adverse events following the treatment given, but more importantly, 2 out of 3 of those patients did not show any growth of Pseudomonas after therapy. And there is a nice video on the Sunday project about the first patient that we treated with bacteriophage, and it was really, it's seared in my memory when I first told the mum and the child that you do not have Pseudomonas in your lung any longer. And we also see an improvement in terms of lung function above and beyond what was expected from the commencement of ETI and previous admissions for pulmonary exacerbation. And with that, I would like to thank my team and all of you for listening to my talk. Thank you.
Thank you, Dr. Dev. Just for housekeeping, we make a note of any questions. We're working towards having a few minutes for questions at the end, and we'll get all the speakers back up. But now I'd like to introduce Professor Adam Jaffe from Randwick Sydney Kids Hospital, and he's going to tell us about the raft of research going on to assist those left behind. I'll leave it to you. Thank you.
Thanks very much. So I'm going to take you on a whirlwind journey. I'm going to give a lot of information. I don't expect you to remember most of it, but what I want you to leave with is this idea of the incredible hope that exists for those 10% of people with CF who are currently being seen as left behind. Really, in our view, these people are not being left behind because we're working hard to find an approach to treat those people with cystic fibrosis who don't have access to the current modulators. Now, I'm absolutely delighted that Claire has given half my talk, which saves me some time, and has described so beautifully how a cell works. In my mind, if you look at a cell, it reminds me a little bit like a library. You've got a library where all your chromosomes hang out and your genes are, and each book is a gene. And in that book, there are instructions written, in, let's call it English, and that, we'll say, for example, make a protein that goes to the surface and opens like a gate. That's your chloride channel. And if there's a mistake in that, a spelling mistake in that book, then when it gets photocopied, that photocopy then is translated into protein that doesn't function properly. And so if you actually look at what happens in the types of different classes, because all these genes are classified into 6 or 7 different classes, it depends on how that protein is functioning. So that, for example, class 1, where the stop mutations, the protein is truncated very, very early, it's about 22%. Delta F508 sits in class 2, where there's one spelling mistake. The cell sees that protein is abnormal and then destroys it, which is why it doesn't head off to the surface and function properly. And there's class 3, which is about 6%, and this was the original G5501D ivacaptor modulators all those years ago, where it's a squeaky gate. The protein gets to the surface and acts like a rusty old gate. And 6% have class 4 mutations, and those are the other ones as well. So 90% of people have access to our current modulators, but they're unavailable for rare and ultra-rare mutations. And of course, there are some people who suffer intolerable side effects as well. So those are the people who can't take modulators. And it's very difficult to do proper clinical trials. We always want a standard double-blind placebo-controlled study, but not if you're the one person in Australia with that gene, because there are thousands of genes, more than 2,000. About 400 of those actually cause CF. So you can't do the classic design, and our regulators struggle with that. And of course, there's inequity, and those from different ethnic backgrounds who have very rare mutations. So these are the potential approaches you can take. So, and I will talk a little bit about gene therapies. You can't talk about those left behind without talking about gene therapies, but obviously they correct the faulty gene. RNA therapies like mRNA, and I'll talk a little bit about something called ASO therapies, which correct the faulty message, that photocopied bit, and then we talk the correctors are actually help get that protein to the chaperone to the surface and then actually function properly. So just a little bit about this. So as Claire said, I was involved in one of the first gene therapy trials using lipids, sort of stuff you put in your face to make you look young. You can actually inhale them into your lung with a CF gene in there to try and replace that. And another approach, as Claire mentioned, was viral as well. Problem is really, really tough. We thought we'd be curing CF within 10 years in the late 90s, and there have been huge studies, but it's really challenging to get to the right cell because the lungs exist to get rid of anything foreign. That's how it's been developed, and so you're trying to get beyond that. So and viruses are really good to get in. Anyone's had a chest infection will know that, but if you get another chest infection or give another repeated application of the virus, the body doesn't like that. It responds with inflammation. And the liposomes really safe, but they're not very good at getting into the lungs. Some studies in the laboratory show if you actually take in modulators and you have gene therapy as well on top, it actually enhances the effect. So that's why we're still exploring a lot of work into gene therapy, because there's additional effects potentially for those even on modulators. And this is probably the largest study from the Brompton, which had 140 people with CF using liposomes. But there was a very, very modest stabilization, and so it hasn't really progressed beyond that. But it was pretty safe. So that's why everyone's pursuing this as an option. With viral vectors, there's so many different types of viruses. There's one called adenovirus, which is where all the work started, but it doesn't work for very long, and you say if you give it again, the body doesn't like it. Adeno-associated virus as well has a good safety profile, and there's a lot of development around AAVs. But actually getting the really big, CF gene's really big, and so trying to deliver the whole gene in a very small virus is problematic. Some groups are looking at lentivirus. Lentivirus is a very interesting virus. Claire mentioned integration. This virus actually integrates into the nucleus, so once it's there, it's there. And so it has some potential concerns that you may get cancer as a result. But it can deliver the whole package of the CF gene. And there's certainly a group in the UK, the Brompton, are really exploring this. And there's some early phase 1 and 2 studies planned for 2024. So a whole group is exploring that. Other viruses people are playing with are bocavirus and herpes virus as well. And you can see a phase 1 study using herpes simplex virus. So it's really finding how do we deliver the gene, what's the optimal delivery package, and so people are using viruses. And Claire put that up. I just wanted to highlight just where we are in phase 1 and phase 2 studies. So far from being confined to the history of science, gene therapy is still cracking on all those years later. And to just give you an idea, there's a phase 1 study underway, and again, AAV, a lot of preclinical studies in the test tube, and you can see here just going through the sort of things that people are looking at, viruses and non-viral vectors. Claire also mentioned gene editing, and that's another approach that's been explored. Very different techniques called gene writing, prime editing, gene coding. These are all new scientific techniques to change the gene. So there's a lot of hope here in the science that is within cystic fibrosis. And of course, the advantage of this, it's mutation agnostic. So it doesn't matter what gene mutation you have, this will overcome it, as opposed to the modulators, which are very specific, aimed at your type of gene. So that's the huge advantage for everyone, including those left behind. And then the other issue is how do we change the RNA and ASO. So ASO is a type of therapy I want to talk about. These are tiny little message RNA, so remember that's the photocopy. And you'll hear a lot about antisense oligonucleotides called ASOs. They're really small pieces of the nucleic acid, tiny little words, in other words, in the sentences, and they actually bind to the message RNA, and you can increase expression, decrease expression, and you can modify genes, and it's already used in some therapies. Spinal muscular atrophy, in our hospital, children who would have died by 8 months of age had one-shot gene therapy, and they're running around at the age of 2. It's quite extraordinary. And so that's one example of a disease which is using ASO. So it's here now, and so people are really excited about it. What's really cool, and this is a slide from Batsheva Kerem, so this, if you look at the mucus layer in the airway, those are the little holes, the pores in the mucus area. That tiny little dot is the size of an ASO. So it actually gets through that mucus layer. It's so small and gets in. So it's and the way it's charged is that it actually shoots into the cell. So very, very clever. And so people are really excited about that. And we all know, as Claire said, about mRNA, because anyone's had a COVID vaccine has been subjected to treatment from mRNA therapy. And again, it's independent of the disease, the mutation that you have. And it doesn't have to get into the actual nucleus. Actually, as Claire says, it's one of the great advantages. And there's various different types of RNA therapies. So you'll hear a lot about this in science in the years to come, an approach to cystic fibrosis. And a lot of examples here. There's a phase 2 study in healthy volunteers, and there's a phase 2 plan for people with CF as well shortly. There's another example from Vertex of lipids, and then some furthermore. Okay. So I'm just going to give you an idea, and really beautiful resources. Anyone interested in the education aspects of genetic therapies, the CF Foundation has done some work, so please have a look there. And that's developed with and co-designed with people with CF. And for example, they've developed resources to actually ask if you approach to be involved in gene therapy trials, questions to ask your researchers and your health practitioners. The other way we're playing in our laboratory is to actually take cells out the body, modify them, and put them back in. So they already do that in cancer with CAR T therapy. Take your own cells out, modify in the laboratory, and put it back there. And we're using a rabbit nasal sinus model as an example. So that's another approach, using people's own cells, so you don't actually reject your own cells as well. So that's the future and what it looks like. But what can we actually do now? We're talking about modulators, and what we have developed is mini organoids in our laboratory called organoids. We take nasal cells or rectal tissue, and we develop little avatars of people with cystic fibrosis, and you can actually use those to predict who's going to respond to a modulator. And that's how the FDA expanded their use of Kaleido using the laboratory technique, and that was quite interesting. But the problem is it's based on a rat cell model, not on human models. And so what we do in our avatars, we can measure the electricity using something called Ussing's chamber, and you can actually measure it by seeing the changes in the ion transport before and after you have modulator. So in CF, because there's no chloride function, it's really flat, and then once you correct it, it actually changes to a normal shape. And then the other test we do is a forskolin assay, and then we take rectal biopsy and grow these little avatars, and we can actually get them to swell. So I'm hoping that the first one might just work. I don't know if the video is going to work. Any chance of clicking on the video for me? Okay, no. Okay, but there's some video. Yeah. So if you wouldn't mind, yeah, would you mind just starting on the non-CF, on the one on the left? Just there, you can see how they swell up when the chloride channel works. That means that's someone without CF. And these are two different people with, if you wouldn't mind clicking on both those ones, with delta F508 homozygous. And you can see the difference here. The one on the left is not working, but the one on the right is looking normal. And so these are two people with delta F508 homozygous. And this is what we're seeing, that just because you've got a gene that should be respond, there's individual variation. And we can talk about why that occurs. But so just because you've got delta F508 doesn't necessarily mean that Trikafta works. It works in the huge majority, but there's a differential response. And so that's really, really interesting. And we can use this to predict who's going to respond. Thank you. And so avatars can help access in various groups. People are using these avatars to gain access to therapy. Okay, I'm just going to finish up. The French are well ahead of us. And they've actually got access. They put everyone who didn't have access to modulators, they just put everyone on it, and 44% of people responded. So these are people who don't have access. When they used little avatars, the nasal therapy, they showed that actually it was really helpful in predicting who's going to respond. And the Europeans are doing this at the moment. It's something called HIT-CF, where they're taking people who don't have that. And we're doing it on Australia. Peter Walk's leading this, something called an organoid Origin 1 study, where we're taking rectal biopsies and we're using Trikafta to see if they respond. So we're trying to gain access. The problem is even if we know people, and I know people who will respond to Trikafta in Australia, there's no way of getting access through the government. Our health technology assessment pathway is not able to do it. You can in New Zealand, you can in UK and Israel. And hopefully the HTA review comes out at the end of the year. We've been really advocating for a pathway to use this technology to get people onto drug. So lots of other things. I'm just going to finish up now. But just to remind everyone that it's not all about the lungs. There's other approaches. This is from the CF pathway, anti-inflammatory, anti-infective, GI stuff. It's all happening for people for all people with cystic fibrosis. So summary. The challenge is to ensure equitable access. We need to really, in my view, embed avatar technology in our healthcare system. We need an HTA that's fit for purpose. We've got many new therapies coming, and really it's one of hope and optimism. And so with that, I'll end there. Thank you.
Thank you very much, Adam. I'm sure you have questions for our speakers. I can't see any on the app, but if you have a question for our speakers, please put your hand up and, yeah, go away. Would you like to ask a question?
Dr. Deb, so when you had that small sample of 3 with the bacteriophages, I hope I'm saying that right, 6, 7 and 11 years that had the Pseudomonas in, you had 2 that had it cleared. That's just amazing to begin with. In the third that didn't have it cleared, what was that attributed to, and where do you go from here to, I suppose, increase the sample size for your research?
Yeah. Thank you. Perfect questions, actually. To answer the first part, what happened to the patient who didn't respond to therapy, I suspect there were a few things that were happening. His level of bronchiectasis was a little bit more advanced than the other 2 children. And they come from a family that have got multiple patients with Pseudomonas, so I think there were cross-infection that was occurring as well. Although he didn't clear his Pseudomonas, what happened, the boy didn't clear his Pseudomonas, what happened was the sensitivity of the Pseudomonas itself changed. It became more sensitive. There is an interaction between bacteriophages and bacteria. Even though it didn't eradicate it completely, it does change the nature and becoming more susceptible. So I'm hoping to bring him back again with, for an admission to treat him with regular therapy to see if that actually knocks off his Pseudomonas as well. Now, where do we go from here? The things that I'm doing at the moment is the clinical trial is approved for 12 and above, but because we've been successful, I'm going to push it down to 6 years and above. The earlier we get onto children onto this program, the earlier we eradicate Pseudomonas, we will have better outcomes. And so I'm quite excited, and obviously we are a network in Westmead and Randwick in the Sydney Children's Hospital network, but we are probably going to enroll patients from other hospitals as well eventually, so it will grow.
Thank you. Any other questions?
I've got a question for you, Dr. Bed, as well. So how was it administered? Was it bronchoscopy or a nebulizer?
So our study is unique in the sense that we are initially administering it via bronchoscopy because it is important to start that cascade of inflammation, of infection of bacteriophage locally. And then it continues to reproduce. The bacteriophage will continue to reproduce as long as there's bacteria in the lungs. And in addition to that, when we added on the nebulization, it is also to help the upper airway colonization of Pseudomonas as well. So we are hitting 2 sides at once.
Yes, two more questions, sorry, yeah.
Probably to Dr. Deb or Dr. Wainwright, I'm not sure who wants to answer. So we've known for a long time about probably antibiotic resistance. I suppose as a parent that we travel CF here in Queensland, I still notice that we are prescribed antibiotics fairly regularly for the cough and viruses. I'm just wondering how we're filtering down the knowledge that we have about antibiotic resistance to the clinical team so that we are looking at new ideas to treat these
I think that's a really good question, and in fact there have been some interesting talks at this conference about the use of antimicrobial therapy in people on modulators, and in the US there are some studies looking at, they're called the STOP studies, and they're looking really at the sort of waiting perhaps for a while to see what happens to patients if you wait rather than start those antibiotics straight away. I think one of the things that we do have to think about though, and it takes me right back to when I was just starting in cystic fibrosis, one of my sort of older colleagues turned around to me and said, cystic fibrosis is a disease of antibiotics. You're going to be using a lot of them, and that really you're going to need to start to feel a little bit more comfortable about using them quickly. And one of the problems we have is that infections still happen, and infections cause inflammation. They cause trouble. We really do have to balance that, and the answer is we actually don't know yet. Okay, we can't start using phage therapy for everybody because we don't know what's down in the lungs for everybody, and the phages need to be specifically sort of provided for a particular infection. One of the problems in cystic fibrosis is that you may have many different kinds of infection in your lung at the same time as well. So as time goes by, you can have a range of organisms, and in fact if you sample the different parts of the lung, you may get a set of different bugs in different parts of the lung. And so it's not straightforward. It's like a zoo down there sometimes, and you know, the point of giving the antibiotics is really to try and get at that zoo and get on top of it and stop the bugs that might be causing inflammation quickly so that you don't get lung damage. So it's a sort of shotgun, it's a poor therapy in that we're just throwing something at it, but we're doing it to try and stop lung damage. And we've actually been quite successful. So if you look at outcomes without modulators, and you look at it without all of these lovely new therapies, even with the sort of rather poor approach we've had, because we've done it consistently and more, perhaps earlier on, we've got to a stage where we've got children who by and large don't have chronic infection. In our clinic here in Queensland, probably only 10% will have a chronic Pseudomonas infection. The studies for Pseudomonas infections are now getting harder and harder to recruit for. And part of the reason for that is that we're really good at getting rid of those early infections. And we're very quick at stopping infection from causing trouble. Not for everybody, but by and large. So it's not perfect, but it's an approach. I'm not sure if that...
Yeah, thank you. We're going to have to wrap up, unfortunately. I'm sure there's other questions in the crowd, and I'm sure our speakers would be happy to be approached after the session, but we have to move on. So I want a big round of applause, please, for our speakers today, Dr. Dev, Professor Wainwright and Professor Jaffe. Thank you so much for your time and for your presentations. In this room, the next session is Mental Health for Everyone, and in the other room, Longer, Healthier Lives. So if we can just move to those rooms for our next sessions, that would be great. Thank you.